So as a brief review, what is teleportation? It is a process to send a quantum state from one point to another point without physically transmitting the physical system. And what is needed? At least for aspect, the first a particular entangled state, second particular measurement basis, and some unitary operators, and as well as classical communication assistance. And the first quantum teleportation protocol was proposed by Bennett et al. In 1993, and they use Bell state as the quantum channel, and Bell state measurement as the sender measurement basis, and Pauli operator as the receiver's unitary operation, and two classical bit assistants. And this is the outline of this talk. We'll talk about the security and encryption teleportation first. So in any quantum teleportation protocol, the sender and receiver do not know and not required to know the information of the teleported quantum state. Hence, basically, they are only a sender and receiver agent. The state information does not belong to them. So there will be a real sender here. I call here Amira, and there is real receiver here, and this is the teleportation agent. So the original protocol requires handing over the original qubit from real sender into teleportation agent. The problem arises when the original information is very important, in the sense that nobody should not know it except the real receiver. And the direct contact of the teleportation agent with the original information make it possible to steal away the information rather than teleport it. The security on the receiver side has been improved by introducing a controller in which this controller can make the teleportation fail if there is something wrong on the receiver agent. However, there's no work that evaluated the security on the sender side. One of the solutions is to encrypt the actual information. For example, we can use BB84 quantum key distribution, that is by generating some secret key to encrypt the actual qubit and use it for teleportation. Actually, it is okay, but it feels like using two different protocols in one job, and we want a unified one. To do so, we develop what we call quantum daemon code. The main idea is to make a particular quantum state from other two different states, and it should be easy to combine with teleportation, because that's our purpose. And this is the pretty much of our protocol. We use GSG-like state like here, and we use some Bell state measurement as well, and some Pauli operators. And this is the ingredient. There are two different quantum states, and what we do is that we perform some Bell state measurement between the two input with the GSG-like state, and that measurement result with being used to perform the correct unitary operation. And as you can see, there will be two output. There will be two possible output 1 and output 2, and generally both output are different, and both output have its own probability. And why is the encryption? So if we want to send a qubit as like this, x0 and x1, instead sending it directly, the sender prepares another two qubit different from the actual one, parameterized by A, B, C, D, and this is complex number, and should be chosen that satisfy this equation. And this is the encrypted qubit. And as you can see, QDP and QTP is very similar. Both use an entangled state as the result and perform Bell state measurement and use unitary operation. Hence, both of them can be combined easily to make an encrypted quantum teleportation. So this is the pretty much of the diagram. So we modify the single sender here into two sender here, and this is the QDP process. And so what to do by the real sender is that to encrypt the actual qubit into two different qubit here, and give that to the teleportation agent and perform the teleportation by performing some Bell state measurement. And here is a controller David that watch over Bob, which is Bob is a receiver agent. And so if there's nothing wrong, David will cooperate by performing some Hadamard based measurement. and then Bob can replicate, can reconstruct the original state with some probability. So with the QDP, we can improve the security on the sender side. So the actual qubit representing the actual information can be encrypted into two different qubits. Hence, even one of the qubit is stolen, the actual information is safe. And as you can see also, there is no decryption process on teleportation, because the teleportation itself is the decryption process. And this protocol has a non-unit probability success value, but the real sender can choose the coefficient such that the probability remain close to 1. And that's the end of the first part. And the second part, I will talk about the interconnection with quantum steering and Bell non-locality. The result of standard quantum teleportation is entanglement. And however, entanglement is found to be more rich. It can be non-local, meaning violating Bell inequality, and it can be steerable, violating steering inequality. So by definition, entangled state is called non-local if its prediction cannot be replicated by any LHV or local hidden variable model, and entangled state called steerable if its prediction cannot be replicated by any LHS, local hidden state model. And for pure state, entanglement, non-local, and steering are coincide. But for mixed state, it is differentiated. For example, if you consider a generalized Bernoulli state like this, which is a statistical mixture between entangled state and maximally mixed state, and this is Q and P is some real coefficient between 0 and 1, and this is the hierarchy. The dark blue is entangled state only. Sorry, the dark blue is a parable state, meaning not entangled. The light blue is entangled only. The yellow, the yellow part is entangled as well as steerable, but the red part is entangled, steerable, and non-local. The two correlation already have some quantifications already. Let's consider a two-qubit system in Hilbert-Smith representation like this. And we can define correlation matrix like this, with T is defined like this. So this is the quantification. This is for steering measure with 3 measurement setting. And this is the Bell inequality for CHSH inequality. And this is for the teleportation, quantified by the fidelity, quantifying the quality of the teleportation. And as you can see, 3 of the quantification is related to R, correlation matrix. So we can make some plots about 20 million random state using GitLab, and the plot show that there is this minimum fidelity threshold that cannot be achieved when the state has 0 steering measure like this. So the other plot also has a similar behavior, that is for Bell inequality. The plot shows that there is a minimum fidelity threshold that cannot be achieved when the state is local. So local here means the CSHS maximum value is 2 or below. So from that observation, teleportation can be used as an alternative method to certify non-locality as well as quantum steering in one go by calculating its fidelity alone. And for the last part of my talk, I will talk about the performance in noisy environment. So the question is, do we really need quantum teleportation? Because in fact, entangled state use should be prepared somewhere in one place and then distributed into sender and receiver. And why not just use that quantum channel for distribution to directly send the qubit from sender to receiver instead of using it for entangled state distribution? So I make some comparison here. The first I call direct transmission. There is a sender called Alice, send quantum state through a noisy quantum channel, and this is the for teleportation process. Prior to teleportation process, there is entanglement distribution, and I take 5 types of noises here. There are bit flip, phase flip, depolarizing, amplitude damping, and phase damping. And I also make some assumption here. There is distance dependent and time dependent. For distance dependent, meaning the more distance travel, the higher the noise. And for the time dependent, the longer the time exists, the higher the noise. And I calculate the fidelity of the transmission for all of them. There is for direct transmission, second for teleportation, but with distance dependence model, and the third is teleportation. Okay. The third is teleportation, but with time dependent model. And I subtract that value and found that for distance dependence model, teleportation is always superior, meaning all the difference is positive. Teleportation has more high fidelity than the direct transmission. However, for the time dependent model is different. This is the graph for bit flip and phase flip. They both similar. As you can see, there is a negative range in here, meaning teleportation has lower quality compared to direct transmission. But for higher noise parameter here, teleportation win again. And the same observation can be seen from another type of noise. So in the time-dependent model, it's not always superior. So the evaluation shows that for the time-dependent model, teleportation loses its superiority in the lower noise parameter, but gain its superiority again in higher noise parameter. And is there any physical system represented by the model? And yes, we found the works in physical review A. There's a work evaluating photonic system that the noise parameter like this, in which if big gamma t is quite small, we can approach it like this, which is our time-dependent model. And so the behavior will be observed on that system also. And this is our work supporting the top. And we have also some other aspect, but we don't have time. The first about unification with quantum error correction that makes self-correcting quantum teleportation. We also extend the protocol by adding a lot of controllers here, and we also reduce resource costs. And that's all for me. Thank you for your time.
So you mentioned that time-dependent error is good, but distance-dependent error is bad compared to the teleportations. What is the intuition behind that?
Okay. Actually, when we perform some teleportation, actually the result is for distance dependence, teleportation is always good, but for time dependent, it's not always like that. It is because teleportation always requires classical communication, and that classical communication requires some interval time, and that will be and that will add some more noise on one of the qubit, and that's why there is a condition where teleportation will lose compared to direct transmission.
Hi. I have a question regarding the teleportation protocol. You mentioned that the sender can tune the coefficient so that the probability for the receiver to get the actual information is close to 1.
Yes.
By trying to optimize this, do we also lose some of the robustness? I mean, is it also easier for the eavesdropper to learn the actual information by doing this?
Yes, that's correct. Because the main security is that like this. So it's depend the success probability depends on the how Amira or the real sender encrypt the actual qubit, and the success probability will depend on that encryption. It can be set so the probability close to 1, but if one of the qubit is taken and all information is stored, so there is some drawback on that. I have also worked to find some middle path that security is acceptable and probability is higher than the lower bound that result in combination of coefficient that make that happen, that can make happen.
Another question? So I have a question about the plot between the fidelity and CHSH violation.
Okay.
So do you mean that there is also some critical value also for this fidelity to show that?
Yes.
Yeah, this one.
Yes. So for a non-local state, meaning does not violate any Bell inequality, we cannot achieve quantum teleportation with fidelity higher this value. So if we use some random state and we don't know how the quality of that state, and we use directly for teleportation and we evaluate that fidelity, and suppose we find 0.95, and it is automatically certified that that random state is non-local.
So, but vertical axis is statistical quantity, right?
Sorry?
Is it correct? I was wondering what is each point. So vertical axis is a statistical average of Bell operator.
Vertical axis, the CQS max.
Operator of the statistical value or not? It's already expectation value, vertical axis?
Yes, only
Then,
expectation.
what is each point?
X point?
Yeah, each point.
Sorry, I didn't get it.
Each point of
Each point?
of
Which
blue
one?
point, yeah.
The blue point. Oh, this is
Yeah.
the state. This is the random
different
state.
ah,
Yeah,
okay,
different
yes,
state.
yes,
Yeah,
yes,
so
okay.
we plot 20 million random
I
state
see,
here,
I see, I see.
and that's the
Okay.
plot.
Okay, thank you. Any other questions? Okay, so if not, let's thank Muhammad again.
Okay, thank you.